The modern power grid moves an immense amount of energy. When a fault occurs on the line, that energy turns destructive, sending a violent surge of current through the system. The primary defense against this surge is the circuit breaker. Its job seems simple: physically pull two metal contacts apart to break the circuit. But opening the breaker doesn't immediately stop the fault. The electrical pressure superheats the surrounding gas, creating a blinding plasma arc that allows thousands of amps to keep flowing straight across the physical gap. Because alternating current naturally cycles in a wave, there is a fleeting moment when that current waveform drops to exactly zero. At this precise instant, the arc starves and extinguishes. The current is dead, and the physical connection is broken. It looks like the breaker has won, but the true danger is just waking up in the invisible microsecond window that follows. The sudden interruption of a massive fault current acts like slamming the brakes on a freight train. It leaves huge amounts of inductive and capacitive energy trapped in the surrounding network. That trapped energy immediately rebounds. The instant the current dies, a high-frequency voltage violently appears across the open breaker terminals. This is Transient Recovery Voltage, or TRV. What follows is a microsecond race between two opposing forces. On one side, the grid is applying a rapidly rising voltage stress. On the other, the breaker is frantically trying to rebuild the insulating strength of the gap between its open contacts. If the rising voltage outpaces the breaker's recovery, the gap breaks down. The plasma arc violently reignites in a restrike, leading to a complete interruption failure and potentially destroying the equipment. To understand who wins this race, we have to look at the math. The breaker's defense is the rate of recovery of dielectric strength. This is the speed at which the insulating medium, whether it's sulfur hexafluoride, air, or a vacuum, can reclaim the space between the contacts. Pushing against that is the grid's offensive line, the rate of rise of recovery voltage. This dictates both the speed and the peak amplitude of the voltage slamming back into those contacts. We can plot this on a graph. This upward curve is the breaker's dielectric strength over a microsecond timeline, creating a hard withstand boundary. This second line is the grid's TRV. If it pierces the boundary before the breaker recovers, we get a restrike. High voltage capacity alone isn't enough to survive. The breaker must have the raw speed to rebuild its internal insulation faster than the grid can apply the stress. How fast that TRV rises is not a constant. The intensity of the race is dictated entirely by the physical layout and specific components of the surrounding power grid. Take a fault physically located near and limited by a transformer or series reactor. This graph shows the resulting recovery voltage. Because of the specific inductance of that local equipment, the fault produces a relatively smooth, exponential, or oscillatory TRV curve. But shift that fault out onto a transmission line, a scenario known as a short-line fault, and the physics change completely. Here we see a much more violent characteristic. The fault creates traveling waves that bounce back and forth between the open breaker and the fault location, generating a brutal sawtooth waveform with an incredibly high rate of rise. Looking at the breakdown of this sawtooth wave, the source side voltage rises relatively slowly. The real danger comes from the line side, which creates that extremely fast, aggressive triangular spike. A circuit breaker cannot be evaluated in a vacuum. Its ability to clear a fault is intrinsically tied to the exact physical location it occupies on the grid. When grid planners calculate a prospective TRV that exceeds a breaker's physical limits, they have to redesign the local system to alter the physics of the network. One approach is structural. Moving current-limiting reactors from the source side to the neutral side of a capacitor bank completely eliminates the initial massive step jump in reactive voltage. Another strategy is capacitive mitigation. Engineers will install surge capacitors or capacitor voltage transformers directly at the breaker terminals. The logic here comes down to a simple relationship. The rate of voltage rise is equal to current divided by capacitance. By increasing the capacitance at the terminals, engineers physically slow the rate of voltage rise. By adding that capacitance, engineers act as timekeepers. They artificially slow the clock on the grid's voltage response, buying the breaker the vital microseconds it needs to recover. To know exactly what mitigation is needed, planners rely on electromagnetic transient, or EMT, simulations. These models predict these hidden TRV stresses, allowing utilities to specify the exact equipment required long before any construction begins. We so often take it completely for granted when a fault is cleared and the city lights stay on. But every successful circuit interruption is an invisible orchestration of advanced physics, precise hardware timing, and rigorous forward planning. An engineer's control over the grid is measured by their mastery of the microsecond, the incredible ability to predict and win the violent race that only begins once the power is cut.